Greetings to you all. I'm Derek Korn, Senior Editor of Modern Machine Shop Magazine. Thanks for joining us today. Today's webinar, sponsored by SolidCAM, will feature a live cutting demonstration that highlights the advantages of an integrated CAD-CAM system, and in particular, the advantages of the company's iMachining technology. This technology can lead to reduced cycle times and tool wear, and it can also simplify programming and enable automated calculation of optimal machining parameters, which we'll see during the demo. And you'll want to be sure to stick around until the end of the webinar because that's when we're going to randomly pick a winner from our list of attendees to receive a Wildcat Trail ATV from Arctic Cat, which looks pretty sweet. Sean Mahmoudez, SolidCAM's COO, will start with a brief introduction before turning it over to Brendan McKenna, Eastern U.S. Business Manager, and Ken Merritt, Senior Application Engineer, to complete the presentation. The presentation will be followed by a Q&A session. It's easy to submit questions, and I encourage you to do so during the presentation. Simply type your question into the question pane to the right of your screen, and we'll do our best to get to all of them. So let's get started. Sean, please take it away.
Okay. Well, thank you, Derek. I appreciate that. I appreciate everybody spending some time with us today. We're going to move along pretty quick and definitely try to make this worth your time. We're basically going to go through today, we're going to talk about SolidCAM's philosophy, and that's leveraging what you already have to make more money, and that's the whole idea behind what SolidCAM does. We're going to go through a real brief history, and then we're going to get to the real nuts and bolts of this thing and the exciting part where we're going to be actually doing some live cutting with iMachining. And then we're going to discuss exactly why what you saw works. We're going to do a Q&A, as we just said, and then we're going to go through the contest results, and I will say that it's the people who signed up for the contest as well as everybody on this meeting today will have a chance to win that Arctic Cat, and I'm extremely jealous because I don't have the opportunity to win, and nor does anyone associated with MMS nor SolidCAM. So you guys are all in a pretty good situation I'm a little jealous of. So let's start. SolidCAM philosophy, if you ever talk to the owner, which I do often, I do have that privilege, and he's constantly saying, our goal is to allow customers to do more with what they already have. And I think that's what sets us apart is that, we're not going to talk about, the new stuff that you need and all this new stuff, and if you had this, you could do this. The idea is to do more with what you already have, and I think you're going to find that refreshing. Now, the first thing is, he did start off, we'll talk a little bit about the history, but he did start off with his own CAD company, and he was doing CAM and CAD, and then he decided, hey, there's a wonderful program out there called SolidWorks. You folks may have heard of it, and we were one of the first to be a certified gold partner. And that is a huge, huge start for us because we said, well, let's let people use that great CAD system they already have to be able to do more, basically putting the CAM functionality right at their fingertips. So we were awarded the gold partner status, and then we were actually given the ability to sell an OEM bundle so that SolidCAM can go ahead and, if you do want the SolidWorks, if you don't already have it, you can do both. Now, the benefits of SolidCAM as a SolidWorks Gold product is that, it's the same style graphical user interface. It's going to feel the same to you. And we do have other products we're going to talk about the integration, and it does hold to those as well. But if you know SolidWorks, I like to say you already know half our program. So if you have a different CAD system and you're going to use InventorCAM, for instance, you know half that program. And by working directly on the model, you're not going to have any conversion errors, no import, export nightmares, no rebuilding data. There's no loss of GD&T data as well. And one of my favorite things is that SolidWorks extends all the way, the associativity all the way down to the G code. So if you make a parametric change to your model, you're not starting over. And that's a huge benefit because you can basically make the change and watch your G code automatically update. And we'll certainly talk a little bit about that later. So the idea here is not just with the software, but we have a technology called iMachining, which we're going to go in real depth, and it's going to save you time on your cutting tools, setting them up. It's going to save you ridiculous amounts of money on those cutting tools because you're not going to go through them nearly as often. So we have customers all the time talking about that, and it really does save them a tremendous amount of money, and it's a very quick return on their investment. And then the idea here is get more out of your existing machines. So the machines you have, you're going to have the cycle times reduced. There's going to be CNC settings that you're not going to have to worry about your machine and cutting, overworking your machine or anything like that, because we do have settings or a wizard that helps you with the settings. So there's an immense savings in the setup time, immense savings in the programming time, because we have a very simplified way of programming. So, and then there's a great quote from one of our customers underneath that says, he hopes that not many people know about iMachining because it helps them so much. Okay, so again, use your existing CNCs and the machines that you plan to purchase in the future. So hit that, Ken. One of the big things that people come to us all the time and say, hey, I just bought a new multi-axis mill, and my current software won't program it. I can't get a post for it, etc. What do I do? So they already have a CAM system that they like, but they can't use it because they don't have a software that can handle it. So whether it's turning, mill turn, some of these real advanced machines out there, we cover that all, whether it's wire EDM, anything out there, multi-axis, a 5-axis, you name it. We're going to be able to outgrow SolidCAM. Okay? Now, here's another thing is that one of my customers, 034 Motorsports, he was talking about, we love to cut aluminum on our machine. That's all we ever thought we were going to be able to cut. But then we wanted to do stainless because our customers want it. So they took their existing machine that they ever thought was only going to cut aluminum and started to cut stainless. It completely changed the way they do business. Now, we also have been getting into things like ceramics. In fact, we have some ceramic companies we're working with now where they won't even talk about what's going on with the advancements we've made in that type of cutting. So, and you'll see why later, but we have a tremendous advantage in cutting not just the hard metals, but also some of the more brittle, really hard stuff like ceramics. So, and if say that you're in medical and you're wanting to use small tools, we can go ahead and use the smallest tools. I've got customers using tools that are almost too small to see, and because we protect the tool and how it's cutting, they can use them easily. And then and Ken's going to show you a little bit about the programming productivity, you're going to spend a lot less time programming with SolidCAM. So again, those are all the things that do more with what you already have is, saving the programming time, using tools that you never thought you could use on materials that you never thought you'd be able to cut, all on your existing CNC machine. Okay, so I'm going to have Brendan take it over and tell them a little bit about SolidCAM, if you would.
Yeah, absolutely, Sean. So, yeah, the nice thing about SolidCAM is that we are still a privately held company. That is the intention moving forward. I know as long as I'm here, I'm going to do everything I can to ensure that. So that's fantastic. Why does that make us unique? Well, one of the things that it really allows us to do is to be very nimble and very forward-thinking without having to go through the red tape of working for some huge conglomerate of companies. We don't have to. We don't have those roadblocks. We can channel as many resources as possible into the software, whereas a lot of other CAM companies out there now are owned by multinational corporations. So we're very forward-thinking, very quick on our feet, very customer-centric when it comes to making changes to our system and allowing for industry trends. You can see here the
Brendan. Just
Sure.
real quick, I like to say that we do what's best for the customers. We don't have to do what's best for the shareholders. And trust me when I tell you, there's a big difference in that philosophy.
Definitely. That's a great point. Absolutely. So, again, just to continue on here with our company history, SolidCAM was founded in 1984. And, again, Sean, I believe, had mentioned that it started as a kind of a standalone product, but then also we realized that back in 2003, we became a fully integrated product into SolidWorks. We became a certified gold partner with SolidWorks. And really what that means is we do have a very close working relationship with SolidWorks and their development staff. We have the best level of integration of any software out there. That's just the bottom line. Of course, I'm a little biased, but I don't mind saying that. And then also in 2005, you see the release of InventorCAM, which we attained the Autodesk certified product status as well. And Ken, okay, great. So in 2008, you can see SolidCAM here had a major expansion. We expanded into North America, and you can see here that we've got direct support and post-processor staff located strategically throughout the country. The nice part about that is our staff is in basically every single time zone. People on the East Coast can take advantage of West Coast support late at night, and of course you can actually go in the opposite direction because we have European support as well. So we do have a direct sales team. We don't work, Ken, could you just go back real quick on that slide? Yeah. Perfect. And so what we see here is we have now been a direct sales organization. We do not have a direct reseller channel, and there's a reason for that. It actually is, it's very convenient. It's more convenient for the customer for us to be able to provide the support directly from SolidCAM. We don't have to worry about third-party resellers, and it really allows us to maintain strict control over the software and how it's being distributed. So we do also offer weekly free training webinars. We do that bi-weekly, and then we also have again some of the best support that's in the business. We have most of the people on our staff are either programmers or machinists or a combination of both. So it's not really just a guy sitting behind a desk, going through a Rolodex trying to figure out the answer to your question. These are seasoned professionals, programmers, machinists, and I myself am very proud to work on this as part of this team and be a part of this organization because our service and support is just absolutely hands down the best. There's no question about it. And the nice part to see here, in this graphic, I really love this. This just gives you an idea of some customers that we have in some key areas, and this is very quickly becoming a map that you really can't see the background on anymore, and I personally am very thrilled to be able to see that. Love seeing those pins just becoming more and more expansive across the nation here. So that's a great graphic. I really love that. So you can see here some of the SIM data research, the market analysis report, and SolidCAM has been consistently named by SimData as one of the fastest growing CAM companies worldwide. We've had some amazing growth over the past 10 years or so. It's grown pretty much exponentially over the course of that 10 years, and it looks like the trend is going to continue. We're really just
year over year we did 40% growth over the previous year last year, 30% the year before that. I mean, every year it's in the 20, 30, 40% growth. This year we're on an extremely fast-paced track, and we don't see that letting up. Now, we get kind of a late start, so you may not have heard of SolidCAM as often, say, a MasterCAM, but boy, oh boy, will you be hearing about us shortly because our growth is just phenomenal.
Well, and Sean, that's a really great point, too. And you have to also think about it this way, is the fact that, companies like, say, maybe MasterCAM or some others, they spend a lot of time and a lot of money on marketing budgets, whereas, they probably should be concentrating a little bit more on the software. We think that aspect of it is pretty important. So, we may not have the biggest marketing budget in the world, but I'll tell you, we certainly have the best reputation. So,
well, and that's a great point. For instance, when you see us at IMTS, if you do get a chance to go to IMTS in Chicago, you won't see us in the CAM pavilion. You'll actually see us in the pavilion next door, because we won't go anywhere where we can't show how SolidCAM makes an impact on the machine time. Pretty pictures on a screen don't cut it with us. It has to be on a machine. So if you ever see us at a show or anything like that, you will see us running on a machine, because that's what's most important, not this thing. Now, I did want to explain a little bit. Stay tuned, because I did not want to, you guys to drift off to death by PowerPoint. We know how that's going to work. We are going to be doing the live cutting now, and so I did also want to explain that we just had a recent development with the contest. We've decided that the winner will be able to pick up the ArcticCat. We were originally going to ship it, but we've worked with ArcticCat, one of our customers, and they're going to be able to walk into the closest ArcticCat to them. They're going to be able to pick it up, and we are paying for the title, registration, and taxes. So I am really, really jealous, as I mentioned before. So, okay, having said all that, Brendan, anything else before we shift over to Ken and the live machining?
I think that's about it. And again, I just want to thank everybody for their time. We know it's tough to break away sometimes, and again, we appreciate the opportunity to be in front of you here today.
All right, guys. Well, my name's Ken Merritt, and I'm hoping everybody can hear me just fine. And I want to kind of take you through what our technology is and how it works. There's actually two components of iMachining that are really what drive its fantastic relationship with our customers. One of them, of course, is the iMachining toolpath, second to none. It is absolutely fantastic, and we're going to spend some time going through the science today of why that works and how it works. The other item is the iMachining wizard, and this makes the programming of iMachining very effective, because in a real-world scenario, in order to program the appropriate feeds and speeds, you would have to take into account a whole slew of data about the material itself. You would also have to know a bunch of stuff about your tool, what it's capable of doing. You'd also have to evaluate the geometry and try to figure out how deep you're going to run your tool in that. And, of course, you would have to know not only the kinematics of your machine, but you would also have to be aware of some of the vibrational characteristics, fixturing and things of that nature. So as you can see, this could be a very, very complex set of parameters that you would have to figure out in order to be able to effectively drive the iMachining toolpath at its optimum level. Now, with the iMachining technology wizard, it takes all that guesswork out. It takes the information from the machine, knows the kinematics, it knows the maximum feed rates and the spindle speeds and things of that nature. It takes the material hardness and machinability characteristics. It takes the tooling information and information about those tools, blends all of those into a symphony of parameters that are very, very coordinated to drive the tool the way you're going to see it run here in just a few moments. One of the things that we kind of like to talk about is finding your way through all of this stuff. If you had the fastest sports car in the world, if you don't have lights, you're not going to drive it at night, right? If you can't see where you're taking it, it doesn't matter how fast it is. It's not going to get you there. So one of the things we want to take you through is this iMachining wizard that we talk about. And as you can see here, the idea is because we have a pre-knowledge of the machine variables, the material variables, and the tool characteristics, we can basically set this slider from a very, very conservative tool path to a very aggressive tool path, and the system is automatically going to balance those parameters for us so that we can very quickly take advantage of that knowledge instead of trying to fumble around and find our way through that. So we're going to go ahead and get into the cut right now. What we're going to do, the safety glass goggle that you see here over on the left upper corner, is a little mold core that we developed for this. And there's a couple of things that I want you to pay attention to as we're cutting, and I'll kind of point those out as we're going through this. Now, little housekeeping, what we want you to know, you should have a split screen. You should be seeing inside the machine right now. You'll see my hand go in there, okay? And that is going to be what you want to look at. You should have a bar between your two screens showing the PowerPoint and the camera view inside the machine. So go ahead and drag that bar and open up that machine view so we can get a real good view of what we're going to be doing here. Now, let me get a couple items set here on the machine, and we'll be ready to rock and roll. Okay. Now, we are in 1018 cold roll steel. That's a 6x4 block that you should be seeing in there. It's a little bit below the screen view there, but that is also a G.W. Schultz HGW 3/8" tool that you're seeing in there. And I believe we are ready to go. We're going to rock and roll. Here we go with the cut. Now, we're going to be cutting very, very fast here, as you can see. We are at 750 thousandths total depth of cut, and we're going to be building a 3D mold core here. And so what you're going to see take place as this tool is cutting is a very, very controlled cutting angle management. Now, you can also see very clearly in the picture here that the chip ejection is extremely dynamic. And that's because we're always staying on the chip thinning side of the cut. Now, I'll take you through some of that physics here in a few minutes and show you how we can do that. But we are currently cutting at 13,750 RPM on a 3/8" tool at anywhere between 180 and 250 inches a minute. And we're doing that at a cutting angle of 45 degrees, okay? Now, the other thing you're going to notice here is notice the repositioning moves are very, very optimized. What we do is during the calculation time of the algorithm, for each movement of the tool, we are automatically updating the remaining stock so that for each reposition move, we know where the material has been cut out, and we're able to move around that with what we call detour moves without forcing the system to go back up to the rapid clearance plane. This gives us a way of very, very effectively repositioning the tool in a very optimized manner. The other thing you'll notice about this as we go further into this cut is we've done an extensive job of regionalizing the cut. Now we're going to go into the cavity portion. We cut the hole right into the model. We're going to just helix right down to 750 thousandths depth of cut. And we're already at 600 thousandths right now. And we're going to take off cutting this with what we call a spiral morph. Now, the idea behind a spiral morph is that it keeps that tool in contact and allows us to get a much better advantage in the cut without having to reposition. But a spiral morph can only go so far within the range of the minimum and maximum cut. You'll notice it switched into our G-slot recoidal, and now it's going back into that spiral morph. See how effective that spiral morph is? When that is done correctly, you can move a lot of material really, really quickly, okay? Now, it'll go through this again. It'll do the spiral morph as far as it can, and then when it needs to, it'll switch back into what we call our G-slot recoidal, which is what you're seeing right here. And this allows us to very effectively reposition that tool, get right back into that next cut, but without ever over-engaging the tool, okay? Now, at this point right now, go ahead.
Oh, yeah, Ken, no, I just wanted to say it's also worth noting as well, like you were talking about the detour moves, where we keep the tool down all the time as it's repositioning. It's also worth noting that the more you do that, and you know, Ken can explain this a little bit more, but whenever you change from a rapid movement from a G0 to a G1, the machine actually hesitates for just a split second. And the more that you're doing that, obviously the more you're adding to your cycle time. So, you know, that again, SolidCAM really looks at those small little nuance type things and makes sure that that doesn't happen, because if you stack up a ton of those moves, you know, that really adds up to quite a bit on the other end of your cycle time.
Yes, it does, absolutely. Now, Again, notice the optimization of the region that we're cutting in. We finished out the inside. Now we move over to the left-hand side of the mold cap core and begin working on that. Now you'll also see it sort of staircasing. You can kind of see that on the right side. That is something else that we do, and there's a very, very powerful reason behind that. We are basically reducing the staircasing effect of the roughing operation automatically. By specifying a user-defined scallop, we can set what we would like to call the near-net finish of this part to be very, very close to what a normal semi-finishing operation might produce, and therefore allowing us, as you're going to see in this case, to avoid the entire semi-finish operation. So not only are we roughing the material very, very quickly from this model, it also gives us more efficiency in that we obfuscated an entire tool path for semi-finishing cut. And you'll see that in a moment. We're going to get some fantastic surface finish going straight to our ball nose because we've established the staircasing so that we don't have any scallops or any staircase height greater than what was established in the program. Okay? Now again, by the way, throughout this entire cut, about the highest that I've seen on a spindle load, and right there kind of took us to it, was about 35% on spindle loads. So because of the way we're managing this, and I'll get back into the PowerPoint here in a few minutes and walk you through some of the physics of what's going on with that, but because of the way we're managing this tool path, we never overload the spindle. You'll also notice, you may be able to hear the sound of the cut. It's a very, very consistent sound, because as we're moving between the minimum and the maximum cutting angle to do our morphing characteristics, we are also modulating the feed rate so that we maintain a very constant chip thickness at the cutting angle. And what that does for us is that stabilizes the load on the spindle and the load on the tool. And again, we'll talk about some of that science in just a moment after you see the finish of this cut.
Yeah, and I'll tell you, I'm not sure how you feel about some of those detour moves, man, but I'll tell you, that's a little scary sometimes.
We call that pucker factor 5. But the beauty of that is it's a very, very safe move because we are calculating that throughout the entire run of that tool path. We're looking at 6 minutes and 40 seconds to rough all of that material out. And now we're going to step in and we're going to do some finishing. Now, I'm going to talk a little bit about what's going on here, and then we're going to move over into the PowerPoint while this is finishing. A lot of people don't think about how a 5-axis machine can be used. We're not cutting a blade here. We're not cutting an impeller. However, we can still take a great advantage of a 5-axis machine because now we can tilt this over on the side of the ball, and we can use a much higher surface velocity area of the tool to do our finishing. And as you're going to see as this goes along, this is going to result in a very, very nice surface finish for us while we're moving very, very fast across here. I'm at 16,000 RPM and about 180 inches a minute doing finishing, and you can already start to see that shine appearing back there. We're getting a very, very nice surface finish on this because we're tilted over at 40 degrees, and we're doing a lead angle of 10 degrees on this so that we're making sure we don't ever put the tip of the ball where it has no surface velocity onto that cut. So something to think about. We not only do a fantastic job in straight 3-axis, but there's also some really powerful things you can do going into 5-axis, even if you're not dealing with engine porting or turbine blades or things of that nature. Okay. So now let me do this. I'm gonna reach in here and turn this air down just slightly.
Yeah, and Ken, I was just going to add there, obviously for something like this, now, of course you could cut this with a 3-axis machine, but again, once you take this part off and you see the surface finish that you're getting, it's also going to just really drastically reduce the amount of handwork that you would have to do to polish that surface.
Absolutely. Yeah, there's so many benefits to it. It's amazing. So kind of trying to get people to think outside the box here. Just because you're not doing, complex aerospace, blades or vanes or anything like that doesn't mean that you can't benefit from 5-axis. And SolidCAM has an absolutely fantastic simultaneous 5-axis module that will do everything you need it to do. All right, so at this point...
Hold on for a Ken. Let me just add this, that you know, we're on a 5-axis, and it's a nice machine, and we'll talk a little bit about that later. But, again, I'll bring up IMTS. We had an old Defiance mill that was meant for cutting wood and foam, and we were just absolutely running the snot out of it, and people were just shocked and amazed. So,
yeah, we love to call that our angry beaver.
The angry beaver, exactly. So, and we were originally supposed to do our stuff today on a sharp mill, a very low end mill, but unfortunately the setup didn't work out. But so suffice to say that whatever machine you have, it's going to absolutely boost it beyond belief.
Sure.
Yeah, and Sean, that's a great point. We're going to get into some of that, some more of that philosophy as we move forward, because I'm sure a lot of people might be looking at this saying, well, geez, you know, do I have to have a super high-end machine to make this happen? And the answer to that is no. We're going to make you more productive. Yeah, we're going to make you more productive with what you already have. So, and we'll show some video of that in a little bit here.
Well, at this point, let's do this. Go ahead and change your screen again. Slide the bar over. Leave this open enough that you can kind of watch this. It's kind of cool to watch all this 5-axis stuff going on. And you'll see as it progresses through here the growing beauty of that surface finish. But let's go ahead and expand the PowerPoint back out. I want to go ahead and get into the science of cutting angle and begin to explain a little bit of the physics behind all this, so you guys understand that there's way more to this than the average person thinks about. Okay. So what we are doing as we're doing this is we're actually managing how the tool is engaged to the material, and we're doing it in a very, very specific way that helps us control a lot of the forces that are applied to the tool and consequently to the machine. Now, one of the things that I want you to be aware of, we're not really cutting steel, okay? It's kind of a misnomer when we say we're going to cut that part. What we're actually doing is what's called plastic deformation, and this video gives us a real clear image of what plastic deformation is. Now, this is a lathe insert that's passing through 1018 cold roll steel, similar to what we're cutting today. And you'll notice this is a finishing tool, 35-degree tool, and you can kind of see under here what I want you to watch. Let me put this into rewind so it'll do it. You can kind of see the material sort of bend under here due to the pressure. That's what's known as elastic deformation. That's the ability of a material to be deformed from its natural state, but once the pressure is removed, it returns to its natural state without deviation. Well, what's going on up here is obviously not elastic deformation. This is plastic deformation, okay? And it's basically a chiseling action against that material. So I want you to kind of keep that in mind as we begin to discuss what is going on with the physics of what's happening during all of that cut.
Are we going to be testing later for that, just to make sure people are paying attention?
Well, we might, you know. Should we make that a criteria of whether or not they win the contest? No.
I don't know. Probably not.
No, probably not. Well, let me get you into this a little bit, because I think this is pretty cool stuff. One of the things that we've noticed in practical examination over the years as we've been working on this and studying it is that as we increase the cutting edge velocity, the actual latent energy of plastic deformation goes down. Okay, and so it makes it much easier to remove the chip, which means we can take a thicker chip. Okay, so we have the rotational velocity of the cutting edge, and then we also have the forward velocity of the tool. And when those two are in balance, the pressure vector on that tool is about like you see it here. Okay, now I want you to think about a knife on a tomato. If you take a sharp knife and just push it straight down on a tomato, it'll cut it, but it's going to squish it too, right? But if you take that same sharp knife and you drag it very fast across the tomato, the knife will virtually fall through the tomato without any effort whatsoever. That's physics. It's a little bit different, but the illustration is very, very much the same as what we're talking about today. As you increase the cutting edge velocity on the flute, you decrease the amount of energy necessary to remove the chip. Now, what that allows you to do is that allows you to increase the chip thickness, which means you can carry more heat off in the chip, which means you can increase the velocity of the cutter. It's going to generate a little bit more heat, but you can then increase the heat of the size of the chip so it takes more of that heat with it. So it's kind of a ripple effect. It rolls up on itself. And of course, there's a limit on that. But let's take a look at a traditional style of a cut. This is a traditional pocket shape. Each one of these sharp corners here, I like to call a compression zone. And this is where, when the tool makes this transition, the tool becomes completely enveloped in the cut. In other words, we get into this type of a mode here where we're in a full slot cutting condition. Now, on the left-hand side of that cut, this chip is getting thicker and thicker and thicker as the flute advances towards the 90-degree quadrant. On the right-hand side, the chip is getting thinner and thinner and thinner. Well, the other thing that happens over here, think about this, as that chip is curling off of this, it's actually going right into the direction that the tool is traveling, and so you wind up getting what's called chip compaction. Now we have conduction that is conducting the heat that's in that chip back into the tool and overheating the tool. And that's why for years and years we've seen that the tooling manufacturers traditionally only recommend 300, maybe 400 surface feet when cutting steel. Well, guys, today we were at 1,400 surface feet in that roughing operation. Pretty dynamic, okay? And we can do that because we're getting a very dynamic ejection over here on the right side. The chip is being ejected opposite the direction of the tool, therefore carrying all the heat out with it, okay? Now, the other thing that happens is as the tool is cutting here, the pressure vector, when it starts out, is pushing virtually directly opposite of the direction of the tool, and it creates a linear or a deflective force on the tool, which is one of the reasons we've never been able to go deep, because we wind up breaking the tool off because we're putting so much linear force on it, okay? Also, as you can see, once we reach the thickest part of the chip here at the quadrant, the pressure vector is pushing virtually perpendicular to the direction the tool is traveling. That creates that flex. We've always had to come back and take a flex cut because of that, all right? So we wanted to kind of get rid of all of that, but there's also something else that happens right here that is very, very powerful. For an instant in time, when that flute crosses the 90-degree quadrant, the effective rotational velocity, that velocity of the cutter, as it relates to the forward velocity, becomes zero for an instant in time, but we still have forward velocity on the tool, so that pressure vector gets flipped to the outside, and now we're pushing inward on that flute and causing it to break. Also creates what you guys have all seen, harmonic vibration. Okay? What you noticed, if you could hear it today, that tool never sounded like it was chattering because it's never seeing this flip. Okay? And that's because our algorithm limits it to 80 degrees of cutting angle and 10 degrees on the minimum. Okay? Now, we've noticed over our tests and over all the times that we've played with this stuff that somewhere between 85 and 90 degrees, we begin to see that increase in harmonic vibration that is relative to approaching that quadrant, approaching that vector flip. So we kept it below 80 so we don't have to run into that. The below 10, we don't ever want to see a cutting angle below 10 because then we get into a situation, that video I showed you at the beginning, where we're using the plastic deformation. We have to have a chiseling action in order to remove that chip. If we just bounce off the surface, then really all we're doing is burnishing and dulling that cutting edge, and that's not a good thing either. Not to mention the fact that at 10 degrees it's not a very efficient cut. Okay? So we control all that with our algorithm. That's one of the things that it does very, very powerfully. Now, I want to talk a little bit about a traditional toolpath and some of the problems that we have with it. Because it's a parallel offset roughing path, notice all these sharp corners. Everywhere that tool changes direction, we get into those compression zones, and because of that, the increased linear pressures, the increased forces on the tool, the compaction, the increased heat, we can only go so deep, and that means most of our fluid of our tool we're not getting to use, okay? And we'll show you a video here in a little bit that kind of demonstrates a little bit of that as well. Also, over the years, one of the things we did, almost every software on the planet did this, was we created a function called trochoidal milling, and it creates these little loops that go into those compression zones in an attempt to try to reduce some of those negative pressures on the tool. And that worked a little bit. It wasn't really the right thing to do, but we didn't know any better years ago. then we came up with iMachining. Now, iMachining is a very, very advanced system, and it uses a completely different algorithm to control how that tool is going to function. This is our D-slot tricoidal, what I was talking about when we were seeing it on the screen. Let me just walk you through. This is the center line of the tool. Notice that it flows down through here. At this point, it actually helixes off the surface, does a high feed rate G1 repositioning move up to here, and then helixes back in for the next cut. Does the same thing, same thing, same thing. So notice the difference here is there are no sharp corners in this tool path. There's nowhere to over-engage the tool. The cutting angle is completely managed all the time. Okay? Now, we do that also with the morphing spiral that I talked about. The best thing about the morphing spiral is the tool is always in contact. Think about it. If the tool is repositioning, it's in the air. You're not making money. If the tool's in contact, chips are coming off, you're making money. Okay? So what we want to do is we want to try to optimize that as much as possible. Now, the spiral morph can be a two-edged sword, and I'll explain that in a moment. But one of the things we do is we use these separation channels, like you see here, to split an area out to where we can spiral morph it. Now the tool can move around it. In this case, from the outside to the inside, means we don't ever run into an internal corner again. Makes it much easier to manage that cutting angle in a way that is very, very effective for the tool path. Now that's quite a difference from the traditional view, isn't it?
Well, you know, that's the other thing, Ken, too. I was just going to point that out. When you look at that picture on the far right, you know, a lot of people might say, well, geez, that looks like a lot of toolpath compared to the picture in the middle. Can you kind of expand on that a little bit?
Oh, you bet, yeah. It is a lot more toolpath if you're only talking about one level. Okay, but let's take a look at this toolpath as being a 1-inch deep toolpath, and I'll show you in a moment some of the things that we did with that. If I do this with a really deep toolpath, I have to take the same pattern multiple times at very shallow depths in order to avoid breaking my tool. I also have to do that at a much, much slower spindle speed and feed rate. And so it takes a lot longer to run that pattern, and then I have to do it again and again and again and again at each of those Z steps. What you saw today, we were cutting at 750 thousandths deep. That's 2 times the diameter of the tool. We've actually cut effectively up to 5 times diameter of tool in depth of cut. So you can do that and take a lot more material out. Yes, it's a longer linear distance of toolpath, but we're doing it so much faster and doing it typically at one level that it makes the toolpath, the overall cycle, much, much more efficient.
Hey, Ken?
Yes.
The other comment that I've heard, that I've heard is, you know, people say, boy, that looks like a much more complicated toolpath. Do I have to set up databases? Is it any harder to program? Because, you know, versus a racetrack or even tricoidal, there's a lot more going on there. How much harder is it to program?
It is absolutely easy to program because you basically select the geometry. Our algorithm figures out where the tool motion needs to be. You don't have to think about that. That's the beauty of the wizard, is the wizard takes into account all of these different parameters we talked about at the beginning, and it uses those to establish how it needs to run all this at the depth that we've chosen so as to not overload the machine, not overload the horsepower of the spindle, not overload the vibration characteristics of the spindle, and so forth. So it's a very, very easy programming scenario, and I can show you that in just a few minutes. Now, I talked about the morphing spiral being a two-edged sword. I want you to understand this. If we took a long, narrow section like this and we simply peeled off that back separation channel so that we could morph all the way around this to a centralized collapse point, then that would become a very inefficient toolpath, because what would happen along these long sides here, we would have to be at the very minimum angle in order to meet the control point here in the center. And across these short sides, we'd be at the maximum, where we'd be getting a very efficient cut. But most of the cutting in that case would be done at or very near the minimum cutting angle and be very inefficient. So what we did is we created another function in our algorithm that automatically analyzes, and again, this is not something you have to figure out. You don't have to do, you know, containment boundaries or anything like that. The system looks at the topology of the area, and it automatically calculates where to break up the zone to create more symmetric regions where we can do the spiral morph at or very near the maximum cutting angle where we get maximum efficiency in the cycle. So it's a very, very powerful feature in the system. Now, we also put a priority on the morphing. If we can morph, we will. So in this case, we're showing an inside out, but we start off with morphing. We're going to deal with what we got to deal with. If there's islands, if there's regions that need to be D-slot tricoidal or channel separated, we're going to do that. But if we can, we're going to switch back into the morphing spiral because, again, when done correctly, it is the most effective way to remove material. We'll deal with what we got to deal with. But if we can, even if it's just for a short period of time, we're going to switch back into morphing so that we optimize every second we can out of your toolpath for you. Now, at some point in the course of most of our toolpaths, we have to switch back into final parallel passes, the D-slot tricoidal. However, one of the things that makes us a very, very strong system is because we can use that minimum to maximum angle, we can morph these passes as well. And so these passes can stay in contact more for a longer distance and do less repositioning, again, increasing the efficiency of that toolpath. We also use those detour moves to try to keep the machine in cut as much as we can and quickly get back into the next cut, optimizing the region as well as the retracts. Now, we also support rest material. Obviously, you could use a bigger tool out here than the rest machine operation is going to come in and do all of our iMachining stuff only in those areas where the bigger tool didn't fit. We also do a function called iFinish, which is very unique, and a lot of people have not found out about this yet, so I kind of want to talk about it a little bit. If this model radius is very near the tool radius, then even with only leaving 10 thousandths of stock on this wall, I can wind up chattering going through this because I actually overload the tool. It's pretty phenomenal when you study the geometry on it, how it works. But you guys have all seen this. You've heard the chirping in the corners. You've seen the diagonal scratch lines going down through here. What that is as that flute is going in there, it over-engages. That causes it to flex out. But that flexing out causes it to pull out of the chip. Now it bounces back against the wall and does it again with the next flute. And so you get that chirping, and you get those diagonal lines left in there. And a lot of times that bounce flex actually overcuts that wall and damages the part. Well, with iMachining, what we do is we analyze all of those regions, find out only those areas where it would over-engage, and we go use our D-slot tricoidal method to pick those corners down to the minimum cutting angle so that when we do come through with the final finish pass, it's a very smooth cut, no over-engagement, no chatter, no chirping in the corner, and a very nice surface finish all the way through these, even with near-net surface size. Okay? Now, before we get into this, let's go back into the machine here for a moment. Notice we're done with our cut. I do want you to see some of this, so let me wheel it back down here. Brendan, it sounded like you were starting to say something.
Well, yeah, I just wanted to. I was just going to talk about the machine here, but why don't we take a look at the surface finish on this before we get into that?
Maybe a good time to look at some chips too, there, Ken.
Absolutely. Yeah. As you can see here, guys, the surface finish on here is absolutely beautiful in cutting this. I'm looking at, I can't hardly feel any kind of scraping on this with my thumbnail. So I'm figuring this is probably in the 16 to 18 RA finish area, and that's with no semi-finishing operation. And I also want you to see, I'll just scatter some of these chips across here.
And by the way, Ken had his thumbnail calibrated just a few weeks ago. So
I always have it calibrated, man. I have a special tool for that calibration. But what I want you to notice about those chips there, notice the consistency in them, okay? Remember I said is even though we're working from a minimum angle to a maximum angle, we're modulating the feed rate as we do that so that the chip thickness remains the same at the cutting angle, whether it's at the minimum or whether it's at the maximum. What that does for you is it keeps an extremely, extremely constant load on your tool because we're removing the same chip all the time, okay? So a very, very effective way of cutting and doing what we want to do here, okay? But very, very nice surface finish all over this.
Yeah, and that's a great point, Ken. And again, that translates over into, you can see here, we've got a picture on the right-hand side here of a machine that is, let's just say it's far less performance than the machine that you just witnessed live.
That's being kind and courteous, my friend.
You know, it's really kind of interesting. I talk to many of my customers who are using machinery that are, quite frankly, probably older than I am, and it's older than Ken, even, if you can believe that.
Hey!
So,
They didn't have.
did they have machines back then? I don't think so. I thought it was like, I thought there was the hammer and chisel method back then. But the question that we get. The question that we get quite often is, do I have to go out and buy a $200,000, $300,000, $400,000 machine in order to have iMachining work for me? And the answer to that question is a resounding no.
A resounding no. Mm-hmm.
Yeah, and this video is a great story, and I'll let Ken tell the story here. But this really shows the tremendous capabilities of iMachining and what it can do for your existing machinery, even older machinery.
Yeah, and guys, this is not a real sexy video, as you can see. Okay, but let me give you the story background on this. This is one of our customers out in Colorado. They called me up and they said, "Hey, look, I need to do something better. This is an old TM1, or might have been a TM2, Haas tool room mill, open bed mill. Thing's been road hard and put away wet many a time. I mean, it's rickety. The spindle's not very sturdy. It only has a 4,500 RPM spindle. It can only go about 50 inches a minute before it gets into the, as you can see, it's kind of hesitating going around here. I'm using all 50 inches a minute of it. But it gets into hesitation when it's doing that. Now, this pocket over here, he was cutting his traditional way, and he was showing me what he was doing. He had to cut this. This is a 3/8 inch tool, and by the way, he even went so far as to buy some pretty decent tools. He was using an OSG Exocarb 3150, and in a 3/8 version, 3-fluter, that is a $68 tool or thereabouts, okay? Pretty decent tool. But he could only do this at 2,200 RPM, 18 inches a minute, and 50 thousandths depth of cut. So with a 1-inch depth of cut, it's actually, I think, 985 or something thousandths. He wound up having to do 20 passes to accomplish that. It took him 2 hours and 26 minutes to make this cut, and by the end of the cut, the bottom 50 thousandths of the tool was completely wasted. Okay? So what he wound up having to do was change to a new tool and take the finish cut around the wall to create the surface finish you see, and then he would use that tool to cut the next pocket. And so he was burning up one essentially $70 tool for every pocket. Okay? Now what I did, as you can see, again, not a very sexy video. Let me ramp it forward a little bit, but look at the chip color here. I'm at 1-inch depth of cut. I'm all the way down, 985, whatever it was. I'm running 4,500 RPM. I'm taking advantage of everything this machine has, okay, even though it's not a whole lot. I'm pushing the 50 inches a minute to the max, and you can see it hesitating here and there, but it's cutting this whole thing out in one shot. Now let's go ahead and go all the way to the end. Look at the chip color all the way at the end of this cut. And I want you to see something here that's really amazing. This blew his mind. 7 minutes and 26 seconds cycle time from 2 hours and 26 minutes. The other thing that was absolutely amazing to him, we took that tool out of the spindle and looked at it under a 3X loop. You could not tell it was worn. I would challenge anybody to have looked at that tool under a loop and tell me that tool had been used at that point. Now, I put it back in the spindle. We cut 3 more pockets on this bar just to see what it would do. At the end of the 4th pocket, the chip color was slightly darker than what you see in here, but it was still gold. And when we pulled the tool out and looked at it, there was some very slight scuffing of the coating right at the flute edge, and there was a shine down the flute where you could see it had kind of worn the coating off of the absolute razor edge of the flute, but it was still razor sharp. And I ran my thumbnail down it. You could not feel any microcracking on that flute edge at all. Now, how many pockets could we have cut? I don't know. I'm going to guess probably around 8 or 10, based on the progression I saw in the chip color from 1 to 4. But he was only getting 1, and it was costing him 2 hours and 26 minutes to cut that pocket. I could have done all 10 in less time than it took him to cut 1. And use the same tool. Okay?
Yeah. You know, and Ken, it's a great point. And just to emphasize here, you know, really what we're trying to get across is the multifaceted benefits of iMachining. Obviously, number one, your cycle times are going to be drastically reduced, but also you're creating much less wear and tear on your machine, less wear and tear on your spindle bearings, and then also you are what you're doing is you're getting far greater tool life. So, when you look at some people would look at the way this machine's and they look how fast it is and they go, wow, that's great. But they don't. You have to kind of take a deeper look and to see what this is actually doing for you. And once you see it and you apply it to what you have currently, that's when really kind of the light bulb goes off and people go, wow, this is just really great stuff.
Now, if you want to get crazy, and I've been accused of being a little crazy from time to time.
Let's get crazy, Ken.
Let me show you this one.
All the time.
And let me tell you, I was laughing the entire time I was cutting this. This is a tool that we've designed. It's got a parabolic ejection cavity, and I had pushed this already on the machine at 350 inches a minute at 12,000 RPM and 60 degrees of cutting angle, and it wasn't even breathing hard. And so I decided, well, let's take it up a little bit and let's see what we can do. Running 14,000 RPM. This is a 10 millimeter tool. 14,000 RPM and 512 inches a minute at 55 degrees cutting angle. That's over 1,472 surface feet on this tool. This is a 3x5 block of steel. We're going to take this down to next to nothing in a very, very short amount of time. And this, by the way, is the second cut on this tool. Okay, and as I said, I was kind of laughing the whole time because I fully expected this tool to break. I was pushing it to its maximum limit and trying to find out where that limit was, and it already cut one, and I was like, all right, let's cut another one, see if we can do another one. And so here it is on the second one, and it's still just tearing it up, okay? Now, obviously, this is not something I'd do in production, but wanting to find out what it could do, I decided to push it to its maximum limit. But look at what we've done here on this machine with iMachining's toolpath. We did all of that cutting on a 3x5 at 800 thousandths depth of cut in 1 minute and 27 seconds. It's pretty phenomenal.
And let me just make the point. This is what senior application engineers at SolidCAM do in their spare time. That's why I said pretty pictures on a screen don't mean much in the SolidCAM world. We're all about machine performance. Again, the people that you'll talk to at SolidCAM, they know machining. They're not keyboardists. They're not just experts in manipulating the software. We have experts that know exactly how to cut. And Ken's pretty modest, but he actually is part of the patents. He invented this tool. So that's the type of people we have, and that's where our focus is.
And one of the things that I do want to mention, by the way, if you guys are using iMachining and you're using level 5, level 6 on the Wizard, and you're gaining some major improvements in your machine, but you're not really pushing it to the limit like I'm doing here, you can get away with ER32 holders, milling chucks, things of that nature. If you guys decide that you want to start really getting radical, you've got some new machinery that's got super high speed and stuff like that, and you really want to start pushing the limit, one of the things I want you to be aware of, don't try to do that with simple holders, because there's a lot of downforce on these tools, especially when you start digging in with a heavy chip thickness. In this particular case, on this 10 millimeter tool, I was using a 4/1000 chip thickness at the cutting edge, and it's a 7-flute tool. So we were creating a lot of downforce on this. That's why I'm using what you see here is the RegoFix holders in here, because they have extremely tight gripping force. Okay, so just be aware. Doing regular mild cutting with it, increasing your efficiencies up to 3, 4, 5 times, you can get away with your standard holders. We're going to take the advantage of what you've got and take it to its very upper limit. But be aware, there's a point where as you start to get more aggressive, you need to start thinking about tool holders and what you need to do. Call us. We will help you with those things. We've got some great connections around the country, some fantastic tool suppliers. I've got a great relationship with RegoFix. I talked about the G.W. Schultz tool a few minutes ago. We've got a great relationship with them. The tool that you saw in the ceramics, we're involved in a patent on that as well. So we have a lot of resources at our fingertips. Call us. We'll help you out.
Yeah, definitely, Ken. That's a great point. Now, one of the other things that obviously we get quite often, and in fact, if you take a look at our website, we just have some great customer feedback. We have some excellent customer testimonial videos up on the website. The feedback that we get from iMachining, it happens on a daily basis, and it really is something that makes my job so fun. Is the fact that the accolades that we keep getting are just are really they're fun to read, and I know it makes Sean happy, and it certainly makes us happy to be able to put these up on our website.
You know what really makes me happy is when I go to YouTube and I type in iMachining and I see some of our customers posting. Now, the language is a little more colorful than the ones that I've used on our website, but there is nothing that I get a bigger kick out of than to hear how just incredibly shocked and happy they are with the results of using iMachining.
Yeah, Brendan, tell them about your favorite YouTube video.
Oh yeah, well there is one that I found, Sean. It's great. There's a guy who it's a cell phone video, and this guy was machining just like crazy, and I couldn't believe it. And then he actually started clapping at the end of the cycle. It was one of the funniest things. I loved it.
Speaking of our website.
Yeah, absolutely. So if you go to SolidCAM.com, go ahead and take a look at the website. There is just an absolute ton of information up there. We have, like I said, the customer testimonials. We have our solid iMachining professor videos. We have getting started videos. There's just an absolute ton of content there. And to take that one step further, like Ken said, go ahead and give us a call. If you want to talk a little bit about the software, you want to take a deeper dive into something you saw here today, you want to see how your part would function within SolidCAM, absolutely give us a call. Our support guys are absolutely amazing. Like I said, they're all either programmers or machinists or a combination of both, and they love talking to people, and we love talking to people. We want to make sure that you're getting the best solution out there, which ultimately is SolidCAM's integration. So we're very proud of our team. Please feel free to take advantage of that.
Yeah, I tell people just even if you're not a customer, just call our support team, 800 number, 8866 number, toll free, and just talk to them because they're the difference. I mean, it's a product too, but they're the difference in the actual model of how we support our customers, and these guys are the best in the business. So, and I'll say this too, due to all that other, we were talking about the customer talk back and forth and all the videos posted. Well, what happened in 2014 last year was that some of the customers for Siemens NX started to say, whoa, why isn't this in my high-end Siemens NX? This is a very expensive system. It's a high-end system, but I can't do what you guys can do in Solid. So what we basically did was we honored that customer request, and this year iMachining for NX is available. We're also due to the kind of the same thing, and that's the iMachining module for NX. It's running right inside, and that's so that they can do the higher end machining, the tool life and the cycle times and things like that. But also Onshape, which many people have been hearing about. Onshape, which is basically the cloud-based CAD. We're also going to, in fact, if you go to their website, you can see that SolidCAM is part of the Onshape. So you'll see the entire SolidCAM available in Onshape very, very soon. So there's a lot going on. There's a question that they asked about PTC Creo. And boy, I'd love to see that in the future. And we're kind of busy bears right now. But did I just say busy bears? Gosh.
You did actually.
It was a long day. Okay. Yeah, I deserve to be slapped for that one. Anyway, we're very busy people, and but I would expect things like PTC Creo in the future, if at all possible, because again, iMachining, the people are just absolutely clamoring for it.
And hey, I just wanted to give a quick shout out to our partners. We do a lot with partners, guys. You heard me talk about GW Schultz, RegoFix. We work with Goering. We work with Herco. We're working with the Hermle people. We're doing some stuff with Sharp. Internationally, we've got several partners that we're working with. But one of them here, Applied Machine Solutions, they're gracious enough to let us use their machines for these type of presentations, and so I kind of want to give them a quick shout out to thank you. We do remain machine neutral, so about the most I'm willing to say right now is my opinion of Herco has changed dramatically over the years. If you're looking for a new machine, I'd say this is one you ought to look at. I'll go that far with it. But if you need anything in the industry, Skip's got some great resources. He's been in this industry for 30 years. He's got contacts all over the place. So you might want to capture this information. If you need coolant, tool holders, work holders, tools, anything like that, it might not be a bad resource for you to take a quick phone call with him.
And there was a question about machines earlier. We have a staff of post writers. I think there's 7 people on that in the U.S. that these guys, that's what they do for a living. Because one of the biggest complaints we hear, why do people come to SolidCAM? A lot of times it's because they can't get a decent post for their machine. They've been promised a library post or an off-the-shelf or a certified post. Well, I can tell you right now, 2 machines that leave the dock and go to 2 different resellers from the same manufacturer can be configured entirely different. And that's one of the big differences, is that we make sure that that post specifically for that machine is working. So that's a big difference. So no matter what machine you have, that's something that we can definitely help with.
Yeah, we'll work with you to dial it into your satisfaction. So.
Okay. Well, Ken, I think we're just about done, aren't we?
I think so. We're a little bit over time. We want to appreciate. The only thing left to be the question and answer. We're about 7 minutes over time, so I think we're okay with sticking around.
There's something else, maybe a little something that we may have forgotten.
Oh, yeah.
Yeah. Everybody on there going, get to it, get to it. They're 7 minutes over. Come on.
You want to give away the money, don't you? Okay.
Well, no, I don't. I actually don't, but I think we need to.
Okay, well, what we're going to do, Derek, are you back with us?
I am.
Okay, I'm going to, once I get this opened up on my system, I'm going to simply begin scrolling from the top to the bottom, and at some point here I want you to just say stop, and whoever's name is in the top row on the screen will be the winner of the Arctic Cat.
And I can tell you, we have all the people who registered for the contest as well as all the people on this webinar, and so they're all in there. And Ken is just scrolling up and down. They have been random number generated, sorted, so they're in complete random order. They're not
alphabetical order or anything like that.
We're doing this as fair as possible, and Ken is just scrolling up and down. And when Derek tells him to stop, the one at the very top gets to win it. I'm so jealous.
Yeah, me too. All right, let me count to 3, and after 3, I'm going to yell it. All right, 1, 2, 3, stop.
Hey, looks like a Brandon Teal.
Okay.
So congratulations, Brandon.
Simmons Machine Tool Corp. Excellent.
Wow, he's
very
in
cool, guys.
Where is 518? I
don't know, but
see if I can borrow it. If he's anywhere near Florida, I'm borrowing that thing.
So, all right, Sean, number 342 is the row registration on that.
Got it.
Congratulations, Brandon. Very nice. I think you're going to really enjoy that. And if we've got time for question and answers at this point, Derek, how are we running? Can we afford to hang on for a few more minutes?
Yeah, we're a little bit over, but I don't think that's a problem.
Okay.
We've got a few here. One question is, can the user easily fine-tune the G code within SolidCAM?
If you have some understanding of structured logic and you want to get into writing the post-processor, yes, our post-processors are wide open. We don't lock them down. So we can teach you how to run the post if you want to, and if you'd like to be able to manage your own, that's absolutely available to you.
But are they talking about editing the G code like what they do at the machine, Derek?
That's what I'm assuming, yes.
Yeah, modifying instead of having to alter it afterwards. Is there a way? I'm sure he's asking, is there a way to make it, flavored to their way of doing it without having? See, a lot of the competitive softwares will force you to come back and pay them to edit your posts. So, no, our posts are wide open.
Well, and the whole idea behind SolidCAM is we don't want to see people at the machine editing code, because if they're editing code, that means, like Ken said, that the post isn't dialed in correctly or something's not working correctly. We want this thing to be as seamless to your machine as possible.
So then, speaking about posts, this person would like to know if you provide posts for small CNC routers.
Yes, we can. Absolutely. We've got a library of literally hundreds and hundreds of posts. One of those will be probably very near what they want, and we can make edits to make it closer.
Exactly. We always edit them.
Another question here. What makes you different than what some are calling peel milling?
Very good question. There's several differences. There's a lot of the systems out there nowadays are claiming that they do the same thing as iMachining because they do narrow radial engagement and high feed rates and stuff like that. However, we have patented several of our characteristics so that nobody else can do those. The minimum to maximum cutting angle, the morphing spiral, the detour repositioning moves, several of those types of functionalities, the ACP, the axial contact points characteristics of our system, those are all patented features, and nobody else can do that. So everybody else is basically doing either a single cutting angle engagement, or they're doing just a standard or constant radial engagement of the cut, and then the toolpath patterns may look somewhat similar to what we're doing, but they're not the same. They don't have the channel separations. They don't have the feed rate modulation for the cutting angle. Most everyone I've ever seen manages the feed rate based on chip load, where we're managing it based on chip thickness, which is
and the wizard.
Yeah,
and don't forget the wizard.
Absolutely.
The wizard's a huge difference.
All of that is a part of the wizard, which makes it very easy to set the system up to make it do what you want to do. In fact, let me just kind of show you real quick here. In the operation that we were running today, this technology wizard gives us the ability, because we know all of these parameters in the background, we can very easily just decide to run very mellow or run very aggressive, whichever you want. And because we have captured machine data, material data, and tooling characteristics, we can marry all of those parameters together in a way that makes sense, that is much, much easier to set up, and that's why we patented the wizard. So I hope that answers that question.
So, yeah, another question here. In terms of, the types of end mills that are probably most appropriate for this type of toolpath, what can you talk about in terms of that?
Well, okay. In general, virtually any end mill is acceptable for this. We're going to, traditional toolpath versus an iMachining toolpath. iMachining is going to make that tool perform significantly better than it will in a traditional toolpath situation. However, you are going to gain more performance out of going to, higher grade tooling. So anything where you're working with, micrograin carbides, you're working with sophisticated coatings like Altin or Nacro or NACO or Tylen, those types of coatings. Higher helix angles tend to give us a better shearing force, allow us to carry a little bit more chip thickness, which allows us to carry more heat off. So any of those kinds of things, I would suggest high-grade carbide, higher helix angles. The tool we were using today was not as high a helix angle as the one that I ran really fast. However, it was a variably indexed and variable helix angle, and that made it run really quiet. Okay, so virtually anybody's tool is going to perform much better in iMachining, but the higher performance tools are definitely going to perform higher.
So let's wrap it up here with one more question. Is SolidCAM offered in an educational environment like a high school or college for free, or maybe at a reduced price?
Sean, I'll let you handle that one.
I'd be happy to. I was answering questions offline. I didn't want you to hear me type in.
I lost you.
Lots of good questions. No, we actually have an educational manager, and we do things a little different. We treat education like it's a paying customer, and I know that well, actually many schools have come to us and say that, XYZ company, they can never get the reseller to return their calls, or they want to charge them a lot. Again, with our direct sales model and our direct support model, we don't have to worry about whether or not we're going to be making a ton of money on the schools. So we actually have a program where, as long as a school has a students, where they're training students, they get our software for free. And that's for 10 licenses or 100 licenses. They get the post free. We spent an ungodly amount of time and money on a curriculum, a step-by-step training manual, and it goes through the CAD and the CAM and SolidCAM. So yes, please contact us, and you'll never pay for your educational CAM again. So, we really believe that, a lot of the success of our customers is going to be the ability to get SolidCAM users in the future, because, that's one thing that, if someone's using MasterCAM, one of the big concerns is, hey, they teach it at every school, I can get, MasterCAM. Well, we have an extensive list of schools now that are now using SolidCAM, and we want to expand that. So absolutely, and we'll treat you like a customer. We're not just going to, treat you like an orphan stepchild. So you'll get support. You can talk to our people. Again, we have the study guide and post-processors. And as far as I'm concerned, I want it to be the strongest educational program out there that there is.
Good deal. Well, that's all the time we have for the webinar. We certainly hope you found it valuable. I'd like to thank all the guys for not only for the presentation, but for fielding the questions we received. And congrats to the winner of the ATV. So on behalf of Modern Machine Shop and SolidCAM, thanks for joining us, and enjoy the rest of your day.
Thank you, everybody.
Thank you all. Appreciate it.